Everything in our universe is made of matter.
Matter is composed of atoms, electrons orbiting a nucleus of protons and neutrons. When physicists smashed atoms together, they discovered even smaller components, elementary particles. But then a problem arose. To see something, light waves bounce off an object and into our eyes, where the brain creates an image. Elementary particles, however, are too small for light waves to contact. When shortened, the waves gain energy and alter the image, revealing blurry spheres. This is the Heisenberg uncertainty principle.
So scientists, unsure of their true nature, imagined particles as zero-dimensional points.
Using this criteria, they developed the Standard Model, in which atoms consist of quarks and leptons that exchange messenger particles to create atomic attractions. Scientists found messenger particles for all fundamental forces in our universe, except gravity. In Einstein's theory of relativity, gravity occurs when planets, stars, and other objects warp the fabric of space. We feel gravity as the Earth follows curves formed by the Sun. Gravity is smooth and geometric, but in the quantum world, space is bumpy and chaotic. Time twists, spatial dimensions distort.
It seems entirely different from Einstein's description of gravity. But to explain our universe in one theory, scientists needed to link the worlds of the large and small.
What could warp and curve in the quantum world? Not a point, but a string. String theory states elementary particles consist of one-dimensional strands of energy called strings.
These strings are incredibly tiny. If an atom were enlarged to the size of the solar system, a string would only be the size of one tree.
Like the strings of a guitar vibrate differently to create different notes, the strings vibrate differently to create different particles.
String theory, however, isn't completely straightforward.
For starters, no experiment has proven the string's existence.
The theory also requires a universe with at least 10 dimensions.
We only experience 3 dimensions of space and 1 of time, so where are the rest? Theodore Kaluza and Oscar Klein propose compactification. This suggests additional dimensions are curled into tiny Calabi-Yau manifolds that affect the string's movements. Another explanation involves brains, higher dimensional worlds, in a 5th dimension called the bulk. We live on a 4-dimensional brain. While most particles are open strings confined to our brain, gravitons are closed strings that move between brains, making gravity weaker in our universe than the other forces. This brain world is invisible since photons can't enter the bulk.
Now, despite these issues, the math for string theory works and has been applied to other areas of physics. Someday, string theory may even lead to a theory of everything.